You ever hear a statistic that just feels a little off? They say numbers don't lie, but let's be honest, they can definitely be used to tell very different stories. Well, today, we're going to put on our detective hats and learn how to uncover the truth. And a very warm welcome to the Flow Tao Salon. In this explainer, we're diving deep into the stories hidden inside statistics. The goal? To give you the tools to see the world just a little bit more clearly. So let's get right into it. All right, our first mystery starts with a single, really simple word, average. It seems totally straightforward, right? But as you're about to see, this one little word can be twisted to paint two completely different pictures. So picture this, a small company, the employees are on strike. A local news crew shows up and asks about pay, but they get two wildly different answers. The union rep says the average salary is 30 grand. The owner insists it's 50 grand. Now here's the kicker. They are both looking at the exact same payroll data. So, who's lying? Okay, let's look at the actual numbers. Here's the raw data. We've got 6 employees and the owner. And you can see there's a pretty wide spread in what people are making, especially when you get to that last number. So how on earth can both of those claims be true? Well, here's the secret. The word average can actually mean 3 different things: the mean, the median, or the mode. The union? They use the median. That's the number smack dab in the middle of the list, which is $30,000. The owner? He used the mean, where you add everything up and divide by 7, which comes out to $50,000. So believe it or not, neither of them was technically lying. That massive salary the owner gets, that's what we call an outlier, and it pulls the mean way, way up, making it a pretty misleading number for what a typical employee earns. This is exactly why you almost always hear about the median income or median house prices. So the big takeaway here, anytime you hear the word average, your first question should be, wait, which average are we talking about? Okay, so now we know that data can be presented in, shall we say, creative ways. But how do we generate numbers that we can actually trust? How do we test if something really, truly works? Well, it all comes down to designing a fair experiment. For this, the absolute gold standard is what's called a double-blind controlled study. It sounds complicated, but it's not. It just means you have 2 groups. One gets the real deal, the other gets a fake, a placebo. And here's the crucial part, the double-blind bit. Neither the people taking the pills nor the researchers handing them out have any idea who is getting what. This is huge because it removes bias from everybody involved. So let's put this idea to the test with a pretty fun example: homeopathic sleeping pills. Homeopathy has this really interesting principle. The more you dilute a substance, the more powerful it's supposed to become. Let's take a look at a standard 30C dilution to see exactly what that means in practice. To get started, you take 1 single drop of your active ingredient and you mix it with 99 drops of water. That right there, that's a 1C mixture. Simple enough. Now for a 2C mixture, you take 1 drop from that first bottle and you add it to 99 more drops of plain water. So now we're at 1 part per 10,000. You can see where this is going. But we need to do this 30 times over. By the time we get to a 30C mixture, the dilution factor is 1 over 10 to the power of 60. That's a 1 with 60 zeros after it. I mean, it's a number so ridiculously big, our brains can't even really comprehend it. Let's try to put that into perspective. If you wanted to have a decent statistical chance of getting just 1 single molecule of the original ingredient, you would need a sphere of this 30C solution that is the size of our entire sun. In other words, the pill you're taking contains nothing. It's just sugar and water. It's the ultimate placebo, and it's a perfect example of why we need controlled experiments to tell the difference between something that actually works and something that's just a really good story. So we've seen how to spot misleading data, and we've talked about how to design good experiments. But where did all these ideas even come from? Well, you might be surprised to learn that modern statistics is actually a pretty new science. I mean, think about it. Geometry and algebra, they're thousands of years old. Calculus got its start back in the 1600s. But modern statistics, the kind that shapes our world every single day, it really only got going in the late 1800s. It's an incredibly young field of science. And one of its earliest pioneers might really surprise you. Everyone knows Florence Nightingale as the founder of modern nursing, right? But what most people don't know is that she was also a brilliant, passionate statistician. She figured out that to get the government to actually do something, she couldn't just throw tables of numbers at them. She had to make them see the data. During the Crimean War, she proved that more soldiers were dying from diseases caused by poor sanitation in the hospitals than from their actual battle wounds. Her charts were so powerful, so convincing, that the government had to act. And the result? The mortality rate plummeted from a horrifying 42% down to just over 2%. She literally saved thousands of lives, not with medicine, but with math. Now, the other giant from this era was a man named Ronald Fisher, often called the Isaac Newton of statistics. And for good reason. He was an absolute genius who basically single-handedly invented many of the core tools we still rely on today. Things like the principles of experimental design and a little something that would change science forever: the p-value. Okay, let's tackle a big one. You've probably heard the term p-value thrown around, or heard something is statistically significant, but what does that actually mean? Well, in a nutshell, the p-value is a tool that scientists use to help them decide if the result of their experiment is a real effect or if it could have just happened by pure random chance. Okay, that's the textbook definition. Let's break it down into plain English. You always start with a boring assumption, called the null hypothesis, which is basically that nothing interesting is going on. For example, this coin is fair. The p-value then asks a simple question. If my coin really is fair, how surprising is the result I just saw? It's basically a surprise-o-meter. Let's try it with a coin flip. You get one head. Is that surprising? Nah, it's a 50-50 shot. Two heads in a row? A 25% chance. Still plausible. But what about 5 heads in a row? Well, the probability of that happening with a fair coin is only about 3%. Now that's a very surprising result. The p-value is low, so our surprise-o-meter is going off. It makes us start to think, maybe my initial assumption that the coin is fair is actually wrong. That's all it is. It's just a measure of surprise. So, we've covered misleading averages, the importance of experimental design, and the ever-elusive p-value. But these aren't just abstract academic ideas. Oh no. This is a powerful, practical toolkit that you can apply directly to business, to marketing, to making better decisions every single day. Let's quickly recap these 3 big ideas and see exactly how each one translates into a real-world business advantage. All right, first up, averages. When you're figuring out your marketing budget, don't just look at the mean customer value, especially if you have a few giant whale clients. Use the median. That'll tell you what your typical customer is actually worth. Second, experimental design. You're probably already doing this. It's called A/B testing. Does that red button really get more clicks than the blue one? Don't guess. Run a controlled experiment and let the data tell you. And finally, the p-value. Before you sink $1 million into a new product launch based on a survey where customers showed a slight preference, make sure that result is statistically significant. You want to be sure you're not just betting the entire farm on random noise. At the end of the day, these tools are about empowerment. They help you move from just guessing to actually knowing. They help you cut through all the noise and find the real story hiding in the data. So the only real question left is, after everything we've talked about today, what data are you going to question tomorrow?